So, let's start. Good afternoon, ladies and gentlemen. Welcome to today's webinar. I am Dave Hui, and your host for today. And today's webinar is to introduce some recent developments and offshore structural vibration control. Offshore structures such as offshore wind turbines and offshore platforms are located at the harsh environment. Environmental loadings such as wind and sea wave may result in excessive vibrations to these offshore structures. It's imperative to control the adverse vibrations of these structures, and today's webinar will introduce some recent development in this area. In particular, the vibration control of offshore wind turbines, semi-submersible platforms, and pipelines by respectively using tuned mass dampers, inerters, and pipe-in-pipe concept will be also introduced. We are fortunate to have with us today a distinguished speaker. He brings invaluable expertise and insights that will indeed allow us to explore the topic today with a fruitful and enriching experience. And now, I would like to introduce our distinguished speaker, Associate Professor of the Department of Civil and Environmental Engineering in the Hong Kong Polytechnic University, Professor Kaiming B.
Hello.
Hello. Dr. B is an Associate Professor, Presidential Young Scholar Scheme in the Department of Civil and Environmental Engineering of the Hong Kong Polytechnic University. Before joining the PolyU in January 2023, he was an Australian Researcher Council Future Fellow and Associate Professor in the Centre for Infrastructure Monitoring and Protection at Curtin University in Australia. Dr. B research interests mainly include structural vibration control, structural dynamics, and earthquake engineering. He has generated more than 170 peer-reviewed papers in the well-known international journals. His research papers have attracted more than 65,000 6,500 citations in Google Scholar with an H index of 48. Dr. B has won quite a few highly competitive research grants, including the prestigious ARC Future Fellowship and Discovery Early Career Researcher Award in Australia. Dr. B is also an associate editor of Engineering Structures. For the next 1 hour together, our speaker will present on some recent developments and offshore structural vibration control. So, ladies and gentlemen, please allow me first to read the agenda for today. Today's webinar will be divided into two sections. The first agenda is the presentation by Professor B. After that, we will have a Q&A sections. So, ladies and gentlemen, let's welcome our speaker, Professor Kaiming B. Welcome, Dr. B.
Okay, thank you, Chairman. Good afternoon, ladies and gentlemen. So this is Kaiming B from Hong Kong Polytechnic University, from the Department of Civil and Environmental Engineering. So you can see my screen, right? So can you see the screen?
Yes, I can.
Okay, and it's also, the moving, right? You can see this PDF file, right?
Yeah.
Okay, yes. So first, I would like to briefly introduce the Department of Civil and Environmental Engineering in PolyU. So that's also, like the requirement from our department. Okay, so briefly, I take about 5 minutes to quickly introduce the department here. So the first introduce about the global recognition of the CEE. Actually, the CEE is ranked pretty high in different, kinds of rankings, including like the QS ranking. We're currently ranked at 17, and for the Shanghai ranking, we are even, the higher. We are ranked at number 2 in the world. Okay, and also we have some other kinds of rankings. Basically, they are pretty, about the top 10 in the world. For this CEE faculty members, actually, we have one member of the Chinese Academy of Science, and also we have one fellow of the Australia Academy of Engineering and Technology, and also one fellow of the Royal Academy of Engineering UK. And we also have like the 7 youngs, the Changjiang Distinguished Scholar, that's Chinese, Ministry of Education. And so in total, our department, we have about a bit more than 40 staff here. And among these staff, we have 26. That's ranked the world's top 2%, scientists. That's released by the Stanford University. So I think this percentage is also very, very high in the world. Okay, so that's something about the global recognition. And also, I would like to introduce some of our, the large grants we recently received. From 2017, in this, about 8 years, we actually received like the 4 theme-based research grants. So that's from Professor Tao Wang, our Jin Guangteng, our president, and also Professor Xiangdong Li, which is the dean of our, the faculty, and also we have the Professor YQ Ni, Yiqin Ni. So he received this grant in the round 2023 and 24. Okay, so altogether, you can see that's about how many? That's more than 200 million, the Hong Kong dollars, about 200 million, right? So so that's about that the theme-based grant, and also we received some other grants as well, large grants like including the Green Tech Fund. Last year, our head, Professor C.S. Poon, and also my colleague, the Shaoyuan Lu, received this Green Tech Fund, and also Professor Poon also received this Lanto, the Conservation Fund. For this, this shows the RIF and also the CIF we received in the last 2 years. So for the last round, Professor Poon again and also Professor Liu again, they received this RIF grant. And for the CIF, we have Professor Yu Dong received this CIF grant. For the year before, last year, so we have Professor Zhu and also Professor Leng received this RIF grant. For this CIF, we have Professor Yong Xia and also Professor Yu Hong Wang. They received this CIF, okay, in this, 2 years ago, received this CIF. And the last one, not the last one, the next one is about these academic programs. We offer the undergraduate program. We also offer the taught postgraduate program, and of course, we also offer the research postgraduate program, which includes the MPhil and also the PhD as well. Actually, we have a large number of the research staff in our department, even though we got I just mentioned about a little bit more than 40, the academic staff. Our research, like the people in our department are actually quite large. We got more than 700, okay, including like the RAP, research assistant professor, like a postdoc, with PhD student, and also some other, researchers. So just a total number is more than 700. Okay. And what's the next? The next is outstanding alumni. We got many, very outstanding alumni. Actually, here I just list some of them that's given by our department. So here I list 6 here. So I will not read the name. I think many of you know them quite well. So I will not read the name here. And for the facilities, we got about 30 laboratories, 2 workshops and also 1 research center that's located in Shenzhen for that research center. So if you check our website, you can find the details of each, the facilities here. Okay, so I will also not give the details because it includes quite a lot here. I just mentioned it got more than 30 laboratories here. All right. So if you want, do some kinds of tests and maybe you can check our website and also check our social the media as well. We've got quite a few social media channels here which are shown here. So if you're interested, you just scan this code here and then you can access them. Okay, so that's something I want to talk at first. So that's a job given by our department to briefly introduce our department. Then I come to my presentation here. I just share this again. So I share my slide. Should be this one here, right? One moment. So this is my slide here. So you can see my slide, right? My PPT. You can see this, right, Chairman? Yes. Okay. Yeah, that's good. Yeah. Okay. Good. Can see this. Then I will go ahead. So today I would like to introduce something like on the offshore structure vibration control. So that's basically what I did in the last couple of years, mainly in Australia, because just introduced by chairman, I joined Hong Kong Polytech like now is about 2.5 years ago. Okay, in the early January of 2023, and so my presentation includes maybe I get this later. Okay, my presentation includes 3 parts. The first one is on this subsea pipeline vibration control, and the second part I will talk a bit about this wind turbine vibration control. Okay, and the last one is on this the platform vibration control. Okay, offshore platform. I will go through them quickly one by one. So the first, have a look at this subsea pipeline vibration control. Basically, here I just introduce some of the concepts, okay, and also the results for the reasons because of the time. Maybe I will not explain too much here. And if you are interested, probably you can refer to my previous papers. You can download them. You can search from my maybe like my Google Scholar and also my personal website. You can find the more detailed information. I will not give too much of the details here. Okay, so. So first, have a look at this pipeline. So this one I propose a sort of this concept is a pipe-in pipe. Okay, by using this kind of design to control the pipeline vibration control. So what is the pipe-in pipe? What is the PIP system here? So based on the name, you can see that it actually includes sort of 2 pipes here, right? So we have an inner pipe and also we have an outer pipe here. For the inner pipe, of course, it's used to transport like the oil and gas, right? So that's basically, this pipe is not new, okay? It's already being applied. We just revise the current design and to achieve our aim. Okay, so this supply has already applied in this offshore industry, especially in the deep sea. Okay, so the inner pipe I just mentioned used to transport the oil and gas, and the outer pipe, because it's in the deep sea, so the pressure from the seawater is actually very high. And then in this case, if you have an outer pipe, so it's maybe sorry, I quit this first. Yeah, then right. So this outer pipe can provide like a protection to the inner pipe. Okay. And these 2 layers of pipe, they are connected by this, this bulkhead and also by this centralizer here. But if you can have a look, so current design, this centralizers is not connected to this, the outer pipe. So that means this inner pipe and outer pipe, they're now just connected by this bulkhead here. Okay, so I just mentioned because of this kind of design. So this pipeline have exceptional thermal insulation capacity, and so it's well suited for the transportation of hydrocarbons that's at the high pressure and also the high temperature environment. All right. We did have some previous studies on this part. Previous studies that's mainly focus on this buckling, okay, because you know the sea ground, so that's not maybe not flat. You got some kind of curve there. In this case, it may cause a buckling problem. Okay, so just the upheaval buckling, and also so if you have some imperfection at the pipe, it will also introduce like the local buckling, and also this local buckling can propagate as well. Okay, so that's a buckling propagation. So that's some previous study, and also because this pipe that's located in the offshore environment, right? And so in that case, I mean, in the offshore, in the subsea, so this pipe might be suspended. Suspended is not fully buried in the soil. So in that case, because you got this suspension span there, so it may may introduce some, you know, the vibration. So that's induced by, for example, the earthquake, and also by this vortex induced vibration can also introduce vibration as well, right? So earthquake, everyone is quite familiar with that. For this vortex induced vibration, I explained a little bit here. For example, now we have a flow, you know, just pass through this you know, a bluff body. So we see this here is a round cross section here. So this one may introduce the transverse fluctuation of this pipe. Okay, that's in the transverse direction due to the periodic shedding of the vortex there. All right, so this one may, because that one may always exist, may threaten the photic life of this pipeline there. So because of this, obviously it's important to control this vibration there, right? Then we introduce this kind of concept I just mentioned. We based on current design, the piping pipe system, I revised this a little bit. And then we form a so-called like a system that's similar to a tune mass damper system. So that's a very widely used system in our structural vibration control like area. Okay, so I just introduced a bit on this. So now, for example, we have a structure. I simplified as a single degree of freedom structure here. So by this, you know, this red one, so it's connected by a spring and also a dashboard. So now, if I want to control the vibration of this this structure, we see the primary structure or the main system here, we can link a very small mass to this primary structure, okay? And the mass ratio between this MT and this MS is normally in civil engineering is less than 5%. Is 5%, okay? So we link a small mass here, but because our civil engineering structure is very heavy, right? Even 5%, that's actually pretty heavy. There is a lot of mass there, okay? So then we can properly select this connecting device. We see there's a spring and also a dashboard there. We can make this structure, this green one, there's a TMD system that's vibrate out of phase with this primary system or this main system there. So it's a sort of this primary system, for example, if it want to, you know, vibrate to the left, so this one may provide the right, this TMD system may provide a force, you know, to the right. Then in this case, the vibration will be cancelled, right? The displacement of the vibration of the primary structure will be you know, sort of cancelled by this TMD system. Yeah, then we can achieve the vibration control purpose. Here, just show you some very simple example here. So this is like a beam without any control, and this one, if we add something here, okay, to control the vibration, if you have a look actually, so this is quite small compared to this a primary system. yeah, right. So as control is the vibration is controlled. But of course, here we just show you a linear system. That's actually more complicated. Okay, so in many of the cases, so here this system may be just linear. So this is a non-linear system. Sorry, I just add a non-linear system here. Okay, but I just want to show you the concept here. All right. Based on this concept, now we can revise this PIP system a little bit. So instead of use that centralizers I just mentioned there in the traditional design, we can sort of use some connections to connect this inner pipe and also the external pipe, the outer pipe together. So in this case, it sort of can form this TMD system. All right, TMD system there to cancel the vibration of each other. And here, I just show you some of the results here. So first, we have a look at this system when it's subjected to the earthquake excitation. So I will not give the details here. Okay, so we got a suspension span here, and I give you this, the different parameters of this inner pipe and also the outer pipe and also the soil spring stiffness as well. And then I just mentioned we should properly select this parameter there. So so that's basically we say that we need optimization here. Okay, for this formula, I will also not talk about this. Okay, but we can base on many, very matured technique and formulas to predict this connecting, these parameters here. Okay, so now this pipe, I just choose three. Typical like the earthquake ground motion with the different, the frequency contents, and we have a look at these results here. So now we can see this blue curve shows the traditional pipe. So that's the inner pipe and outer pipe, they are not connected with each other. So now if I connect them together, in this case, we can see this outer pipe, the vibration is obviously controlled. Okay, so the interesting thing is that for the inner pipe, which functions as like a TMD system in this as a TMD in this TMD system, okay, tuned mass damper system. So for this normal, the TMD system, we actually didn't pay too much attention to the vibration of that small mass here, okay, because normally we need it vibrate very severe. We need like a large vibration there to dissipate energy, to more effectively dissipate energy. Okay, we didn't pay too much attention on that one. We allow the vibration of the TMD system. But if you have a look at this proposed like pipe system, actually you can see this inner pipe, the vibration is also reduced. It's also reduced. Okay, and that's actually something we want, right? Because I just mentioned the inner pipe is used to transport the oil and gas, right? The carbon, the products, yeah. So we don't want that inner pipe to vibrate very seriously, right? Because we also want to protect that as well. So what's the lead to this kind of difference between this PIP system and also that traditional TMD system? That's because of the mass ratio. Okay, I just mentioned for this traditional one, normally we use about 5% mass ratio there. But for this sort of design, you can see that inner pipe and outer pipe, the mass, they are almost at the similar level. Okay, about it can even reach more than 100%. It's a ratio. Okay, so that means the vibration in this case, because of the large mass ratio, so it can significantly reduce the inner pipe vibration as well. Okay, so that's actually the benefit, and also to improve the robustness of that system. Okay, so just for one like example, when it's subjected to the earthquake loading. So now I give you something on that vortex-induced vibration. I think I need to a bit faster because I got quite a lot of slides here. Maybe I cannot finish all of them. And so now it's already 5:30 here. Okay, for this vortex-induced vibration, actually, we don't have this kind of test before. Okay, all of these previous studies, the rigid pipe there is a rigid pipe there. So it's only one layer of pipe. We can say it's one layer of pipe there. So then how to validate our, the analytical model? We can, okay, now I just mentioned, now we use something to connect them together, right? So if I assume this, this stiffness is very large, then in this case, we can consider these two pipes vibrate together. So that's a rigidly linked together, right? So if we derive the equation of motion of this PIP system here, and now I assume this stiffness is large enough, then this system can be simplified as our traditional, this like one layer of pipe system there. And then we can have a look at our result here, okay? So just some tests on that, rigidly connected system here. We can see this black curve is the experimental study, and this red one is we solved by our equation of motion. So that means our equation of motion is actually correct. Yeah, okay. So now we can change this rigidly connected pipe to a pipe, with the optimized spring stiffness and also the dashboard there. Then we can have a look at this control effectiveness here. You can see actually this concept is quite effective as well, right? So we can see when you modify this vibration amplitude, is much smaller compared to that like the traditional one there, right? And we further did the safety simulation there. And so that's for the validation. I will not talk too much on this, and we can see. So that's in the time domain and also in the frequency domain results under different reduced velocities, basically the velocity of the flow, right? So we can see both of them in the frequency domain and also in the time domain. Both of that, the response are reduced. So further demonstrate the effectiveness of our concept. And also the experimental study, we also did a bit on this. And so this is sort of the design again. So that's we can see if without the control, that's a bare cylinder there. We got this sort of peak. So and if we use a flexible rod, we use sort of optimization there. So you got the least, the response there. So demonstrate the effectiveness again. So all right. So that's the one concept. We use the PIP system to control that. And actually, for this vortex-induced vibration, we know that if we change, the shape of the pipe, it can also, change the formation of the vortex there. It can reduce the vortex-induced vibration. So based on this, we can change. Actually, we don't use a round pipe, but the circular. This pipe here, we make this the outside is like a textured pipe. Okay, then in this case we also did some the numerical simulation, and so now if this is our smooth pipe, so now if our design becomes the texture pipe, we can see that this amplitude is become smaller there. It becomes smaller there, okay? So that means it's effective, right? We can further combine these two concepts together. So now the external pipe is the texture pipe, and also the inner pipe, we have an inner pipe as well. Then it becomes the textured inner pipe system. Now, if we have a look at these results here, so we can see this is a single cylinder, so that's a smooth cylinder. So now if it becomes a texture cylinder, we can see that the vibration is become smaller, all right? And now if we further use this PIP system here, so that's actually the vibration is the smallest. Okay, sorry, I think maybe you cannot see this very clearly because this simulation, the size is pretty large. Okay, so the slide of my PPT is more than 300 megabytes, so maybe not that smooth. Okay, I just show you, these results in the time domain. I think that's more clear. Okay, you can clearly see on the different velocities. Maybe this one is even the clearest here. So now if it's a smooth, a single pipe, right? So you got this kind of results. So if we change it to this texture pipe, so this one is the reduced, right? So if we change it to this textured PIP system, so this result is even smaller. So because we use two kinds of mechanism there. So one is the tune mass damper mechanism, as just mentioned, and also the texture pipe, which can change the formation of the vortex there. All right, so that's the first part of my presentation. So basically, I propose a sort of a new revised the traditional design of the pipe-in-pipe system, we connect them together, become a revised pipe system, and then we use that to control the vibration induced by earthquake and also by this vortex as well. And our numerical and also a bit of the experimental study demonstrated that this concept is the effectiveness, is the effect. All right, so that's the first part. For the second part, it's on this wind turbine vibration control, okay? Because now we talk about the green energy, right? So carbon neutralization. So offshore wind turbine, so that's a key to achieve this goal there, actually, right? So if you have a look at this installation here, we can see that that's also increased very sharply recently. And this information actually is not the latest, okay? So now I think I didn't get I didn't check, actually. I should check this, but I haven't done this. And most of this installation, actually, you can see is in our mainland, okay? So the trend is actually, of course, is from the small dimension to the bigger dimension. We can see this, the height is become larger and larger. It become higher and higher, and also from the onshore to offshore, right? Because offshore we got the high quality wind there, and also from the shallow water to the deep sea to the deeper water there. And because of this, the change, we need to maybe the fixed type is not enough. Maybe we need to develop the floating type of wind turbine there. So I will not give too much details here. So and for this, kind of structure, we can see that's very tall and it's a thin-walled structure. So and also we have a very large mass at the top of the wind turbine. From the structure engineer point of view, so actually we this kind of structure is quite vulnerable to the vibration, right? Because we only have a single pipe. I mean the tower there to support a very huge mass at the top of that tower. So if our tower is failed, so this structure will collapse, right? Actually, we got a lot of accident of this wind turbine structure. So here you may remember last September, right? That's in Hainan, right? We got the typhoon Mo, right? So which induced the collapse of quite a few wind turbines there, right? So how to control this vibration of this wind turbine is also a big issue. So this topic, I think, is become pretty hot on the research on wind turbine. It become pretty hot about about 10 years already, I think. So I did a bit on this vibration control. So like the previous studies, normally they can use simplified models there to for the analysis, okay? And for this kind of model, they just lump, the with the nacelle, the mass of the top part, as the lumped mass at the top of the tower, but ignore the rotation of this, this blades there. Okay, but actually we can see that if this wind turbine is operating there, so it's because this blade now is periodically rotated there, right? It will introduce, the centrifugal stiffness to the system. So actually, your frequency vibration characteristics of this structure is not fixed anymore, right? So in this case, assume that the parked condition, which means your wind turbine, this blade is not rotating, maybe not accurate enough. So I just investigate like the influence of the operating condition of this wind turbine here. Okay, and also we investigate some other parameters like the soil structure interaction and also the influence of the seawater here. Because of the time, I will not introduce the last two. Okay, I just introduce this operation condition here. So have a look at this result. Okay, before I introduce the result, because maybe I introduce about this loads. The load, okay, on this structure, we consider the wind load, okay, on the tower, and also so that's how the wind load how we get that, okay. And also we consider the wind load on the blades. We use the BEM method. And also we consider the C wave load. So that's on the monopile. What we consider is the monopile type, okay? The wind turbine there. And sometimes we even have the earthquake. When I talk about the control, we have the earthquake input, okay? And now if we have this kind of, the input, that's the external vibration sources. And if we have a numerical model, and then of course we can get the response there, right? We can calculate the response, the fragility, and even we can do the control, and also maybe, even for the design as well. So now have a look at these results, all right? So this, I just mentioned, I just compare these two different conditions. One is the operational and one is the parked condition. So this table show you the results, okay, of the vibration frequency of this wind turbine here, okay? So maybe just have a look at this column here, okay? I just show you put like a red, rectangular here. So 3 boxes here. So that shows like the first tower fore and aft, frequency. That's a side-to-side frequency for the tower as well. And another one is the blade frequency, okay? For the other frequencies, probably you don't need to pay too much attention to that, because these three, I will use that to explain some of the results later. So that's why I sort of highlighted them here. But you should pay attention to this. These results are obtained based on this parked condition, because in our software, we cannot calculate, that a system with a periodic, like the stiffness change there. It's not easy to calculate that, okay? So that's for the frequency for the parked system. And for these wind loads, we can see that that's for the parked conditions, the edgewise and the flap-wise, the two directions, the wind loads, they're quite similar. But for the operational conditions, then this one becomes different, okay? And also for this operational condition, we can see that these results, they are much higher compared to this parked condition, okay? So that means if our wind turbine is operation, yeah, so that wind load is higher compared to the parked condition. Because of this, large excitation, of course, the response of this structure is also higher. You can see this from this, like the displacement here. That's quite obvious here, right? So when this wind turbine is rotating, we can see that the results, the blue curve, is higher than our, the red curve here. So that's for the tower top in the fore aft. Fore aft is in this direction, okay? This direction, the outer plane. Okay, if you see this, that's the in-plane direction, okay? In terms of that blade, that's out of plane direction. For the side-to-side direction, you also have this kind of results as well, okay? And so just in the time domain, in this frequency domain, you can also see similar results. So I just maybe emphasize, you may pay a bit attention to this frequency I just mentioned here. So for this parked condition, you can see this, there's a peak here, right? The peak here, which corresponds to this 0.603. So that's a flat-wise, the vibration frequency of these blades there. Of this blade there, okay. For that rotational one, you can see actually we cannot find this corresponding, this peak corresponds, the corresponding frequency of this peak here. Just as I just mentioned, when this system is rotating, so it's not that easy to directly calculate the vibration frequency here. Okay, and so that shows the results of the tower. Actually, you can see I just mentioned this second one. This second peak is the vibration frequency of the blades. Okay, it's not that corresponds to the tower, which means this coupling between this tower and also the blades. So we'll introduce, some response to this tower as well, right? So that's quite obvious because of the coupling there. So that's for the tower response. And now show you some of the blade response here. Blade response, also the parked condition and the rotation condition. So it again, for this rotation condition, the result is much larger. So that's in the flap-wise direction. Okay, for the side to edgewise direction, so that's the in-plane direction. Okay, edgewise direction, we can see that if the wind turbine is in the parked condition, the blades 2 and 3, which are here, the response are larger than this blue curve. That's blade 1. Yeah, okay, because that's blade 1 is lower than this blade 2 and 3. So the wind load on these two blades are larger than that one in this blade 1. Okay, so that means the results it will become larger. But for this in-plane, because of the rotating, it's periodically rotated there, so there's no difference for these 3 blades anymore. And then you got the same results here. Okay, and also you can see this in-plane rotating is much higher compared to that displacement of the parked condition there. So that's about the response. So what about the vibration control? The control. All right. So now, if you have a look at this wind turbine there, okay, obviously, so this wind turbine sort of suffer from the higher vibration mode. The higher vibration mode is excited, right? Because we know that for this kind of a structure, the fundamental vibration mode is this first mode is something like this blue curve there, right? And now, if you have a look at this vibration, actually the largest part is sort of at the top part here. It's not at the top, but sort of at the middle part, right? It's located somewhere here. So that just corresponds to the higher vibration mode, for example, the second vibration mode, right? So in this case, if we have the earthquake loading, so because of the earthquake, the frequency contents is even wider. So this higher vibration modes of the structure might be excited. So in this case, not only to control the the fundamental vibration mode, maybe we also need to control the higher vibration mode as well. So if we want to control the fundamental mode, we can put a tuner mass damper I just mentioned, TMD there, put here and at the top, right? So now, if I want to control the higher vibration mode, for example, the second vibration mode here, I should put a TMD at this location B, okay, to effectively control that, right? So we further consider another scenarios. So that's we further divide each TMD into three. That's to further to consider if one of the TMD is malfunction, is not function well, the other TMD may function well, right? May have provided some control effectiveness there. So that's why we propose this sort of 3 designs there. Okay, and all of the mass, if you add them together, so that's the same as this our this single TMD case. Okay, so that means we keep the mass of each case, they are the same, but we divide that. Like in this case, we divided that into 2 TMD. So this one, I even divided that into 6 TMD there. Right. So now we have a look at this control effectiveness. So that's how we optimize the connecting device. Yeah, we're not introduce that. Okay. So so now this is the control effectiveness. Okay. So we consider the wind wave and also earthquake loading as well. And this earthquake loading comes in at the 30 seconds. Okay, and it lasts for 40 seconds there. Okay, because the wind and the wave, they're always there, right? So it's always there. So we the whole duration we calculate 100 seconds, but the earthquake only comes in at the 30 seconds and it lasts for 40 seconds here. So now we have a look at this response here, all right? So of course, if we have the earthquake loading coming in, the structure response will become higher. So that's quite obvious, right? So that's a blue curve is larger than this red curve here. And also, if you have a look at this, the location A, which is at the top of the tower, you can see that the majority energy, is here, right? It's here. The frequency corresponds to the tower frequency, right? And so if you have the location B, if we have an earthquake comes in, we can see that the higher vibration mode, the second vibration mode is also excited, and we have the energy. You can see here, we have the energy is also concentrated at this frequency. So now I use TMD to control that. Okay, so what's the control effectiveness? Yeah, maybe I quickly show you this, the results just by using this table here. I divided that into two, cases I just mentioned. So this one is for that's when the earthquake exists. Okay, for this period, so we only have the wind and the wave here, So this shows the control effectiveness here, right? So if we have only single TMD there, we can see that. So that's give you the best control effectiveness, all right? Because I just mentioned if your loading is only wind and wave, so it's only the fundamental vibration mode of the structure is excited, so right? So now if you have 2 TMD and 6 TMD, the purpose is to control the second vibration mode, right? The mass for the first TMD is become smaller, and of course, then the control effectiveness is becomes smaller as well, right? So that's explained why this not that effective compared to this single TMD case. But now, if we consider the earthquake loading here, we can see that actually now if I divide that into 2 TMD and 6 TMD, then in this case, the control effectiveness is become more evident. All right, so that's because your higher vibration mode is actually excited here. Now I use more TMD, I can control the higher vibration mode. Of course, the control effectiveness it becomes more evident there. All right. And for the blade, I will not talk too much. Will not talk too much on this. It's the same like the results. So here is a brief summary. So basically, I talk about two things here. Okay. So one is the influence of the operational condition on the structure response. So we can see that if we consider the operational condition, the response will be much higher normally compared to our parked condition there, okay? And also we propose using multiple TMD to control the vibration of the wind turbine structure there, all right? So that's the second part. So I need to quickly finish my third part here. So third part is on this inerter, okay? So maybe I create this. Inerter is we see is a two-terminal device. Maybe, I think we still need to explain this a little bit. Okay, so for our traditional like the vibration control device, if you're familiar with that, so normally we change the the damping term, and also maybe we change the stiffness term of the equation of motion, okay? But normally we will not change the mass term here. So in 2000, about 20 years ago, 25 years ago, that's Professor Smith in the University of Cambridge in UK. He proposed like a concept that's a two-terminal device. And they said the force provided by this device is proportional to the the acceleration of the between that the acceleration difference between that two terminals. Yeah. So if you have a look, if we have this kind of a force and we write that into the equation of motion, so that means we can actually change the mass term as well. And Professor Smith gave a name of this device that said is the inerter. Okay, so that means the significance of this device is what is it completed the vibration control theory. So now, normally I just mentioned, traditionally, we only change the stiffness term and also the damping term of the equation of motion. So now we can change the mass term to control the vibration as well. Okay, to vibrate the equation of motion as well. So that's a significance. And actually, this topic is very hot in recent 10 years as well. We published a review paper in about 4 or 5 years ago. I think now receiving more than 300, almost 400 citation now, 300 already more than. So so that means a lot of researchers actually are interested in this kind of work, okay, working on this. And so I need to emphasize the properties of this device. The one is the mass amplification effect. Okay? So I just mentioned for our traditional vibration control, we can add a TMD to the structure, right? And the TMD mass normally it can be not more than 5% of the structure, right? So I just mentioned if you're like this is shows the Taiwan 101 tower there, okay? Because of the mass of the building is huge there, so in this design, they use a ball sort of to control the vibration. So you can see that the mass of this ball is more than 700 tons. It's also very big mass there. So because of this big mass, so it's very difficult for the installation, for the maintenance. It's not that easy. Okay. So now, if we use this, inerter, we can significantly reduce the physical mass of this inerter of this mass there. Okay, so that's because it has a mass amplification effect. Okay, so and another one is the negative stiffness effect. I will not talk too much on this because I didn't introduce too much on this in my presentation, but I did work a bit on this area. We have a different, many methods to realize this, like the inerter. I will not read them, but what I focus on is this ball screw type. Okay, so this mass, okay, we see that's B. We normally see that's a parent mass. It's not the physical mass, it's a parent mass. Okay, so this one with the unit that's a kilogram. Okay, so it's the same mass, it's same unit of the normal mass. So if you have a look at this equation here, if I want to increase the mass of the parent mass of this one, we can actually reduce the lead of this ball screw here, or we can increase the moment of inertia of this, a flywheel here, okay? Actually, this physical mass, theoretically, it can be many times, 1,000 times, 10,000 times, than the physical mass. Here, okay? So that's why we can reduce the physical mass. For the current, the applications, so we mainly, the previous study mainly focus on the analytical study, okay? But we did have some, like the application in engineering practice, like in Japan and also in China as well. And now we use this kind of concept to control the vibration of the offshore semi-submersible platform. Okay, so that's a SSP. We can see that actually the vibration of this platform is pretty severe, right? So and especially in the heave motion, okay, and also the pitch as well. So I just talk about this heave in the vertical direction, okay, heave motion. I use this to control that. So normally for this platform vibration control, we can use a fixed heave plate. Okay, so that's to add like a heave plate at the bottom of this structure to increase the draft displacement of this structure there. Okay, so that's a commonly used method, and this mass is normally very large. It's about 15% of this the structure there. So I just mentioned the TMD concept, right? Some researchers they propose, instead of rigidly connect this mass to this to this top structure, to this SSP, they can use a tuned mass. They said it is a THP, tuned heave plate. So that means that they use a spring and a dashboard to connect them together, and based on the TMD concept. Okay, and so now that's their method, traditional method. Now we propose to use what's that? Our inerter. We see the rotational inertia damper. We connect that to this system. So we analytically, derive the equation of motion, right? So this device actually have two effects. One is because it's rotated there, okay, it's rotating there. Then it provides the damping force rotating in the water. So that the damping force is large, and also it has a mass amplification effect. Okay, so I just mentioned that. So after we know the force provided by the device, then we can derive the equation of the motion of the whole system after I apply that device to this SSP, and we can get the transfer functions for the fixed heave plate for this our RID, our inerter device, and also we can get the corresponding, the transfer function for the heave tuned heel plate. But of course, this one involved the optimization as well. But I will not talk too much on this because of the time here. So I just show you like the parameters we use in our study. So the SSP, we have the mass that's 26,000 tons. Okay, and for the heel plate, if we use heel plate, that's about 15% of the SSP mass. So if I use the RID here, so I use a very small mass actually. So that's only about less than 0.1% compared to this one. Okay, so that's a much smaller, much smaller. So now we have a look at the analytical results. We consider 6 different, the loading scenarios. Sorry, it's almost 6 o'clock. So I mean, the chairman, is that okay? I'm over time a little bit. So is that okay?
Okay, thank you.
Yeah, okay. I try my best. I think I can finish that within about. I hope I can 10 minutes. Okay, so I quickly finish this. So this is the results under the 6 the different scenarios there. We can see that actually after we applied our this RID system for most of the scenarios, it's more effective than this FHP and also the THP device here. Okay, but I want to emphasize that our mass is much smaller compared to that, the FHP and THP, because that's 15%. What we need is only about 0.1% mass of that SSP here. So the different control effectiveness, that's because of the different, the loading conditions. Okay, different loading, they have the different, the frequency content there, which lead to the different control effectiveness there. So that's in the frequency domain. In the time domain, we also have the similar results here. Will not emphasize too much. So just show you the final results here. So if you have a look at this RID, if you use this device, the control effectiveness, that's between about 44 to 75%. For these, is higher than other two kinds of device. All right, and then so analytically we demonstrated this is effective, and then we did the test, device test. Okay, I will not introduce too much on that. So here shows actually shows the very obvious negative stiffness effect. Negative stiffness is we know the positive stiffness, right? Positive is we push something, so the object will against your pushing, right? But for the negative stiffness is the opposite. That object will help you push. Okay, so if it's a positive stiffness, we see that the stiffness normally in this fourth and third quadrant, right? But now it's in the second and the fourth quadrant. So that means this negative stiffness. All right. So so that's the one without water. So if we put that in the water, we can see that because of the water, it's rotating there, it will further dissipate energy. We can see that becomes fuller. So that means the area becomes larger. For this both case, actually we don't put on that turning plate there. Okay, so now if we put our turning plate there, we can see that this is become the even fuller. Okay, because it can dissipate a lot of energy by the water. And also we sort of propose a mechanical model for this device. Because of the time, I will not introduce that. Maybe I ignore this part. And okay, we sort of validate the proposed model is accurate. And we further did some experimental study on this, offshore, the platform, offshore platform, by using the device there, right? So so this you can see that's what I did when I was in Australia. That's in Curtin University there. All right. So we design this test, and we also manufacture this device here. So we carry out the water flume test. We consider like the different loading scenarios, the 14 regular waves and also 2 irregular waves. Okay, 2 irregular waves there. So now we have a look at the effectiveness here. Okay, so that's for the FHP, for our fixed heel plate. That's our traditional method. So this one, that's a traditional method. And also, if you use RID here, you can see this small thing is rotating there, right? So that means it's working there actually. Now we can see some of the control effectiveness there, the results here. So this the black one is a no control. So now if we add our FHP, we can see that it's reduced a little bit, but not that much actually. But if we add our RID, so I think the reduction is a bit more evident. It's more evident. But I just mentioned that mass is quite small compared to that FHP. Yeah, okay. And we can see that by more evidently by using this is RAO curve there. Okay, we can see that at this resonant frequency, which you get almost the highest response. We can see at this area we got this most evident, the control effectiveness there. Right, in the frequency domain, that's these results. In the time domain, you got the similar results. We can see this RID, the red curve, give you the smallest results here, and that in the frequency domain, again, you get that. Okay, so that's the third part. I briefly, quickly finish this. So we sort of introduced a inert device for this semi-submersible platform vibration control, and we demonstrated its effectiveness through analytical study and also through the experimental study. So we found actually it's effective. Okay, but of course all of this that's in the lab scale. We haven't we didn't have any real application yet. Okay, so that's a final summary. So my talk, I briefly introduce what we did in the last maybe 6-7 years. So on the vibration control of a pipeline, subsea pipeline, we propose the pipe-in-pipe concept, and also in the vibration control of offshore wind turbine, and finally on the vibration control of SSP. That's pretty much what I want to talk today. Thank you very much. Sorry for the time. Yeah, sorry about that. Yeah, thank you.
Okay. Thank you, Dr. B, for giving us the full information on the structural vibration control. And now it is the Q&A sections. So if you have any questions, please feel free to raise your questions in the Q&A box. Thank you. Any questions? Please feel free to raise.
Maybe I didn't give too much detail there. Yeah,
So we have one questions. So there's a participant asked the RID for SSP, whether it is required to secure in the sea floor.
yes, that's right. That's you get that. Yeah, so that's a design of that one. We connect that actually to the sea floor. So that's actually okay. So this slide here, all right. So we needed to, because I didn't give it too much detail here. So if we want this inert device most effective, normally we should connect one end. So that's to the ground, okay? Because based on the force provided by this device I just mentioned, is proportional to the relative acceleration between that two terminals there. Okay, so if one end is fixed, yeah, so that give you the best control effectiveness, and then in this case, actually, we want to make this very effective. Then we also sort of need to make that connect to the sea floor as well. And I in our paper actually we try to address this, why this is sort of feasible here. So now here I also put it here, but I didn't have time to explain that. Okay, so for our fixed platform. All right, so I first talk about this fixed platform. Fixed, which means you have this truss here, is directly fixed to the sea floor. right? So for this kind of platform, we normally say in the shallow water, if your water depth is less than 1,000 feet, yeah, we can use this fixed platform. But obviously, if that is very deep, this truss structure, the connection structure here should be quite large, because you also have other kind of loading in the horizontal direction as well, right? So the most effective, the design for this fixed platform is when your water depth is less than, we say, 450 feet there. So between that 450 and 1,000 feet there. So basically, we sort of need like a large, the dimension there. So we sort of propose this kind of design now. We cut that the truss structure there to install this our proposed device. So it's a form of sort of like maybe cannot say the SSP anymore, right? It's a sort of between a fixed platform and also a floating platform there, because it's a bottom part is basically connected to this this seafloor there, right? So that's our argument. Actually, we emphasize in the paper is in the application how it's applicable. Actually, I think we can also discuss that. We for a academic like write papers, and also for training PhD students, that might be okay. But how applicable, actually, we still have a lot of issue. And also, I'm welcome, for any kind of suggestion here. Yeah, thank you.
Thank you, Professor B. And as the time is limited, so I think I can only allow one more questions. And the question is about uh, in Dr. B's perspective, what are the challenging issues or promising directions in the field of vibration control?
Oh, okay. So that's actually, I'm also thinking. I have worked on this area for quite a now maybe about 10 years, a bit more than 10 years, I think. Yes, I'm also thinking on this. It's like I don't know. So for this kind of area, for this traditional one, I think the framework is already like well established. So um, uh, many, like all of these studies cannot uh, break this framework, because it's already, for me, I think it's very established. I don't know how to make a breakthrough that this well established framework here. So like for this why this inverter is a bit is hot recently, I think is one of the reasons is that it provide another option for like the for this vibration control, because we can change the mass term I just mentioned there, right? Normally we just change the stiffness and also the damping term there. So we have one more option. So now a lot of people actually working on this. So in terms of the direction, I don't know, maybe I think we can, now we have some other like I know a lot of people working on different kinds of device. Like for myself, I also work on some other device, like the negative stiffness device. Uh, Maybe I also work on something on that meta material, right? So how practical? That's also an issue. To be honest, I think this question is also I'm thinking, but I still don't have a very good answer to your question, unfortunately. Okay, I think maybe later we can discuss, and I got my email here, and also maybe you can even call my number here at the end, at the very end. Yeah, here I got my email here. Okay, thank you.
Okay, thank you, Dr. B. And ladies and gentlemen, as time's up, so thank you for your participation today. And if you have any further questions, please feel free to you can contact using the email on the screen. And thank you for today coming and have a good day. Thank you.
Okay, thank you everyone. Good night. Thank you. Okay, bye bye.
Bye bye.